Hello, this is the Section 2.3 lesson. In Section 2.2 we introduced the idea of random variables and distributions, and we introduced one specific type of distribution, the simplest of all, called the uniform distribution. In this section we're going to introduce two more specific distributions we call the hypergeometric and binomial distributions. These distributions apply to random experiments that meet certain requirements. So let's define our first type of distribution called the hypergeometric. So consider a random experiment that meets the following two requirements. Number one, we select n objects from a population of capital N without replacement. And then number two, the capital N objects are of two types. Call them type 1 and type 2, where capital N1 are of type 1 and capital N2 are of type 2, and of course N1 plus N2 has to equal capital N. Okay. So we're only dealing with a random experiment that meets these requirements. We're selecting some objects from a larger group without replacement. Notice the emphasis there on without replacement, and we have two types of objects. Okay. So we're going to define the random variable capital X to equal the number of type 1 objects in our sample of little n. Okay. So then X has a so-called hypergeometric distribution, and its probability mass function is given by this. So little f of x is, by definition, the probability that capital X equals little x, and we can calculate it using this formula here. And so these are all combinations. It's a combination times a combination divided by a combination. And our values of x can go anywhere between 0 and little n. Obviously, in a sample of little n, you can't have a negative number of type 1 objects, and you can't have any more than little n type 1 objects. Okay. Now, these numbers, capital N, little n, N1 and N2 are called the parameters of the random variable. And that's a term that we're going to be using frequently throughout the rest of the semester. A parameter is simply a constant that's used to identify or that's used within the distribution or the probability mass function. So to illustrate this, let's look at this simple example. A manufacturer of radios receives a shipment of 200 transistors, 4 of which are defective. To determine if they will accept the shipment, they randomly select 10 transistors and test each. If there is more than one defective transistor in the sample, they reject the entire shipment. Find the probability that the shipment is not rejected. Okay? So notice what we got here. We got a large group of objects, in this case 200 transistors. We have two types, defective and not defective. 4 of them are defective, 196 are not defective. And we are going to select 10 transistors, and we'll do that without replacement because we're not going to test the same one twice. And we want to know something about the probability of a certain number of defective transistors. So we're dealing with a hypergeometric distribution. Okay. And so first of all, let's define our random variable. Capital X is the number of defective transistors in the sample of 10. That's what we're really interested in, the number of defectives in our sample. Okay. So then X is a hypergeometric distribution. We've already identified that. Now we need to identify the value of its parameters. Well, capital N is the total number of transistors, that's 200. Little n is the number that we are selecting, that's 10. N1 is the number of type 1 objects. Well, a type 1 object in this case is a defective transistor because that's what we're interested in. And we have 4 of those. And then N2 is the number of non-defective transistors, which is 196. So now we know what type of distribution we're dealing with, and we know the values of its parameters, and so now we can use those numbers to calculate our probability. So we want to know the probability that the shipment is not rejected. That's the question that's being asked. So now we think about what does that mean in terms of our random variable. Well, it's not rejected if we have 0 defectives in our sample or 1 defective in our sample. So we want to know the probability that x equals 0 or x equals 1. And so in terms of our PMF, we simply need to calculate f of 0 and f of 1 and add those two together. And so we plug in the values of our parameters, the values of x, into our PMF as shown there. And then we do that arithmetic on our calculator. We get those numbers, add them together, and we get our probability of 0.986. Okay? So there's about a 98.6% chance that our shipment will not be rejected. Now, before we define our next type of distribution, we're going to define something that we call a Bernoulli experiment. So a random experiment is called a Bernoulli experiment if each outcome is classified into exactly one of two distinct categories. And this is the key word here, two distinct categories is the important phrase. To have two distinct categories to be a Bernoulli experiment. Now these two categories are commonly called success and failure. Success does not necessarily mean that something good happened, nor does failure mean that something bad happened. Success is a generic term for meaning that we observed whatever it is we're interested in. Now, continuing on with this definition, if a Bernoulli experiment is repeated several times, so we do it over and over again, in such a way that the probability of a success does not change from one iteration to the next, the experiments are said to be independent. So if we do it over and over again, the probability of a success does not change from one time to the next, and we say that the experiments are independent. Okay. Now, a sequence of n Bernoulli trials is, by definition, a sequence of n independent Bernoulli experiments. Okay, so this is kind of a technical definition. N Bernoulli trials means that we repeat something over and over again, and the probability of a success does not change from one to another. An example might be like flipping a coin. We flip a coin, we're either going to get heads or tails. If we consider tails a success, the probability of a success doesn't change from one trial to the next. So flipping a coin a bunch of times would be a sequence of n Bernoulli trials. Now, we're going to use this idea of Bernoulli trials to define our binomial distribution. Okay? So consider a random experiment that meets these two requirements. So a sequence of n Bernoulli trials is performed, and the probability of a success on any one trial is p. So we're going to perform something over and over again, and we're going to let p denote the probability of a success on any one trial. Now define the random variable x to be the number of successes in the n trials. So in this definition, we're interested in the number of successes. So then x is said to have a binomial distribution, and its probability mass function is given by this. Little f of x, by definition, is the probability capital X equals little x. It's equal to n choose x times p raised to the x power times 1 minus p raised to the n minus x. And here our random variable can take on values from 0 up to n. We can't have a negative number of successes, nor can we have more than n successes in n trials. Okay. Now this type of distribution has two parameters, n and p, and the phrase x is b of n comma p means that the variable x has a binomial distribution with parameters n and p. So we're going to see this phrase come up a lot throughout the rest of the semester. So b stands for binomial. The first number is the value of n. The second number is the value of p. So let's do an example to illustrate an application of the binomial distribution. So if a family with 9 children is randomly selected, find the probability of selecting a family with exactly 4 boys. Okay. So let's define the random variable x to be the number of boys in the family, because that's what we're interested in. Okay. Now, the next is to observe that x has a binomial distribution with 9 trials and a probability of a success of 0.5. Now, how do we know that? Well, think of each child in the family as like a trial. It's either male or female, boy or girl. And a success here is a boy because that's what we're interested in. And we're going to assume that the probability of a success is 0.5. So each one of our 9 children is a Bernoulli experiment. We have 9 trials. Probability of success is 0.5. So we're dealing with a binomial distribution. Okay. So now once we've identified that, we can easily calculate our probability. We want to know the probability of exactly 4 boys. So we need to calculate f of 4. We plug things into our PMF, and we get our answer of 0.246. So what that means in a practical sense is that about 24.6% of all families with 9 children are going to have exactly 4 boys. Now these two distributions are very similar, and sometimes it's difficult to determine which type of distribution we're dealing with. So let's just kind of summarize these two distributions. So in a hypergeometric distribution, we are selecting items without replacement. And we have 2 types of items, and we want to know the probability of a certain number of one type. Okay. But in a binomial distribution, we're not selecting items. We are repeating independent trials. We're doing something over and over again, and the probability of a success does not change. Now we have 2 categories of outcomes. Not 2 types of items, but 2 categories of outcomes. And we want to know the probability of a certain number of successes. And so again, these 2 types of distributions are similar. To determine which one to use, ask yourself, am I selecting items or am I repeating independent trials? If I'm selecting items, then it's a hypergeometric. If we're repeating independent trials, then it's a binomial distribution. Our last concept in this section is a fairly simple idea, but it's extremely important because it forms the theoretical foundation for a lot of what we do starting in Chapter 5. And we're going to state this in what we call the unusual event principle, which says if we make an assumption or a claim about a random experiment and then observe an event with a very small probability based on that event, called an unusual event, then we conclude that the assumption is most likely incorrect. Okay? So we start off with an assumption about something, and then we go out and we observe something in the real world, and if that observation has a very small probability based on the assumption, then that's an indication that our assumption is probably incorrect. Now, the next thing we might ask ourselves is, well, just what do we mean by a very small probability? Well, we're going to state that here in the unusual event guideline, which says that if x is binomial and represents the number of successes in a random experiment, then an observed event consisting of exactly x successes is considered unusual if one of these 2 inequalities is true. So the probability that capital X is less than or equal to x is less than 0.05, or the probability that x is greater than or equal to little x is less than 0.05. Okay. So we need to calculate either this probability or this probability. If either one of those is less than 0.05, then we consider that event to be unusual. Now you may ask yourselves, where does that number 0.05 come from? And there's nothing magical about that number. It's just a number that's commonly used, and we're going to see this number come up a lot throughout the rest of the semester. So let's apply this to an example to illustrate what this all means. Suppose a university student body consists of 70% females. To discuss ways of improving dormitory policies, the president selects a panel of 15 students. He claims to have randomly selected the students. However, one administrator questions this claim because there are only 5 females on the panel. Use the rare event principle to test the claim of randomness. Okay? So let's look at what's going on here. We got 70% female. So that means that if we were to select 15 students at random, then about 70% of them should be female. Well, that's what, about 10 students that should be female. But we didn't get 10 students. We got a lot fewer. And so that's an indication that maybe these students weren't randomly selected. And so there seems to be some validity to questioning the claim, but we want to test it a little more formally. Okay. So first of all, let's define our random variable. Let's let x equal the number of females on the panel of 15. Okay. We define this random variable because that's what we're interested in, the number of females on this panel. Okay. Now, if the students really were randomly selected, then x would be approximately binomial of 15 trials with a probability of success of 0.7. In this case, the success is getting a female. If randomly selected, that probability should be 0.7. We have 15 trials, so x is binomial. And so the observed number of successes was 5. That seems a lot smaller than it probably should be. And so we're going to calculate the probability that x is less than or equal to 5. Well, x less than or equal to 5 means x equals 0, or 1, or 2, or all the way up to 5. And so we need to calculate those probabilities by plugging in the values of our parameters. N is 15, p is 0.7, to our PMF. Then the probability that x equals 0, 1, 2, or 3 is very small, practically 0, and so that's where we get these numbers here. Those probabilities are technically not 0, but they're so close to 0 we'll call them 0. This is the probability that x equals 4, the probability that x equals 5. If we add those up, we get 0.0036, and that is much less than 0.05. So because that probability is so small, we would our conclusion would be to reject the claim of randomness. Okay? Now that doesn't prove that students were not randomly selected. It's just enough statistical evidence to reject this claim of randomness. Now lastly, let's talk about how we can do some of these calculations on the calculator. The formulas for the binomial PMF and binomial CDF are built into the calculator. So if you turn your calculators and hit the second and then the vars key, you see the vars is right below the down arrow key, and that will select the distribution menu. And inside of that you see two different submenus, the DISTR and then draw. Under the DISTR menu, you scroll up or down to option A, and you see binom PDF. Now this is the formula, the built-in formula for the binomial PMF. Now we call it the binomial PMF, the calculator calls it the PDF, but it's the same thing. Now the syntax for this function is binom PDF n, p, x. Now if we want to calculate a value of the binomial CDF, we would do the same basic thing, except we would choose option B for the binom CDF, and the syntax is basically the same. So as an example of this, let's look back at this example 237, where our random variable x is the number of females on the panel of 15, and then if randomly selected, then this random variable x would be approximately binomial distributed with n equal 15 and p equals 0.7. So for instance, if we wanted to calculate the probability that x equals 0, meaning the probability of getting exactly 0 females on this panel of 15, we would enter this syntax, binom PDF n, p, x. Here x equals 0, that's the number inside the parentheses. And so if you hit enter, you see this result right here, 1.4 e negative 8. Now that e negative 8 means scientific notation, means times 10 to the negative 8. For all practical purposes, that means this probability is practically 0. And so that's why we wrote down we wrote down 0 for this probability when we did this example. Now in this example, what we actually calculated was the probability that x was less than or equal to 5. Now we can do that by calculating the probability that x equals 0 and x equals 1 and x equals 2, 3, 4, and 5, just like we did on the previous slide, add them all together and get our result. But to calculate a probability like this, where we have x less than or equal to some number, we can actually use our CDF formula. So if we choose the option binom CDF, enter n, comma p, comma x, here x is 5, that's the number inside the parentheses, hit enter, it calculates all 6 of those probabilities, adds them up, and gives us this result here, 0.0036, which is exactly the same thing that we got calculating things earlier. So there we go. That's all there is to calculating binomial probabilities on the calculator. Now there are no formulas for the hypergeometric distribution built into the calculator, so you have to do those kind of manually. But formulas for the binomial distribution are built in.